Okay, so now we're really going to get into the mechanism of how that is brought about, how that force generation or that contraction is brought about. So this is called a sliding filament model, or the sliding filament theory, and I talked about why before because no one has actually ever seen this, but it's a very reliable theory of how muscle contracts. We're going to speak about cross-bridge cycling, which is how we make contact between actin and myosin, drag actin to the M line, and then break that contact. And we do that again and again and again until the muscle fully contracts. We're going to speak about excitation-contraction coupling. This is really how calcium plays a role in turning contraction on and turning contraction off, right? The presence of calcium and that troponin complex, I told you that's going to come back again and again, is how we turn on and turn off muscle contraction. And then we'll speak about some metabolism and fiber types and things like that. So muscle contraction is basically a shortening of the muscle. Okay, muscle is a contractile tissue, and so at the level of the sarcomere, which we just saw, is where all of this shortening really begins. There's the overlap of the thin and thick filaments, and neither of them shorten. Okay, the early physiologists who began studying this thought that the myosin heads actually contracted, or the actin actually contracted. Now we know that that's not true. Right? They are contractile proteins in the sense that they slide past one another, but their length never changes. They do not contract individually. They simply slide or move past each other, okay? So the filaments slide past each other, and neither of them change their individual length. Okay, so within a sarcomere, we'll talk about the events of what happens in the relaxed state and then in the contracted state. So think about this being muscle being relaxed, nice and stretched out, and then this is the state of muscle being contracted. So when that entire muscle shortens. Now we know the A band stays the same in length. I mentioned this earlier. So the A band being this area of overlap where myosin is laying over actin, that never changes, again, because actin and myosin never change their lengths. All they're doing is moving past each other. And so if one is moving in this direction and one is moving in that direction, that length, that change basically cancels out, okay? And so the A band always stays the same. The I band, however, will shorten, okay? As myosin slides this way, or drags actin this way, the A band here will shorten, simply because actin is moving closer to the middle of the sarcomere, closer to the M line. Okay, so the I bands shorten, and we can see that here. The H zone shortens, again, because myosin is moving closer to the M line. So it's dragging actin closer to the M line, and so we can see that the H zone becomes smaller, shortens. And the entire sarcomere shortens effectively, okay? So the sliding is due to the cyclical breaking and forming of these cross-bridge bonds. So the connection between myosin, or the thick filament here, and actin is that cross-bridge cycling. So it's going to make contact with actin, drag it closer to the M line, it's going to release contact. It's going to make contact again, drag it, and then release again. And that cyclical process is what brings actin closer, shortening the A band, shortening the M zone, but shortening the I band, shortening the H zone, but the A band remaining the same. Okay, I hope that makes sense. Any questions on that? Okay, so again, we look at a histological appreciation of this. And again, in the relaxed state up here, this is a sarcomere, and in its contracted state down here. So again, the I band here, which is this lighter staining region around the Z line, okay, this is the Z line, this shortens, we can see that here. That's because actin is being dragged to the M line. The H zone, which we can see here, also shortens because myosin is moving closer to the M line. And then the A band we see remains the exact same. So the A band, or the area of overlap, stays the same. Okay, let's move on to speak about cross-bridge cycling. The cyclical formation of bond between actin and myosin. This results in the sliding of actin towards the middle of the sarcomere. Now the myosin head has two configurations. It has a high energy form. This is when it has ADP and an inorganic phosphate bound to it. In this state, it has a high affinity or a high attraction for actin. It really wants to reach out and bind to actin, okay? Remember, they're going to bind on those two binding sites we talked about. There's a myosin binding site on actin, and there's an actin binding site on myosin. There's also that ATP binding site on the myosin head, right? That's the area that energizes this process. So in the high energy form, myosin has ADP and a phosphate bound to it, and it's really energized. It's really ready to give this energy to this process. It has a strong affiliation or attraction to actin, and it really wants to reach up and bind to actin. In its low energy form, it has ATP bound to it. And although we may be tempted to think because it has ATP, it's in a higher affinity for actin, that's not the case. And when ATP is bound, it's in a low energy form, okay? It doesn't want to interact with actin. It doesn't have a strong affinity or attraction to actin, okay? And so the energy to actually move this relies heavily on the hydrolysis of that ATP. So the breaking of that ATP into that ADP and that inorganic phosphate is sort of that energy waiting to be donated. So in the ADP and phosphate form, we've already cleaved that ATP, we've hydrolyzed that energy, and it's sitting there waiting to give that energy to this process. So the high energy form is going to be ADP and the phosphate already hydrolyzed, okay, already hydrolyzed. Okay, now a way to sort of describe this, a really interesting analogy is rowing. Okay, so if you're rowing and you're in a boat and you have your oar paddle, we can think of the oar paddle, right, that's touching the water as the cross bridge of the thick filament, the myosin head. And the linking of the thick filament to the thin filament is synonymous to your oar paddle touching water. Okay, a very similar process, a very similar machinery. So when your oar paddle touches the water, this is where actin and myosin make contact, okay? Now, the power stroke is where myosin drags actin towards the M line, okay? And so you can think of that as you moving water behind you. So again, if you're in a boat, you reach your oar paddle out into the water. When it makes contact, that's like actin and myosin making contact. When you drag some water behind you, that is the power stroke. That is where myosin drags actin towards the M line, towards the center of the sarcomere. And so the thin and thick filaments then detach. That's where you lift your oar out of the water, okay, and you're going to reposition it to a new place, and that is what myosin does. It's going to break contact with actin, it's going to reposition, it's going to bind to a new actin, and it's going to drag that even closer to the M line, okay? So a very interesting analogy of rowing or moving an oar paddle in water and actin and myosin making contact, dragging actin, making contact again, dragging it again, and so on and so forth. And that happens over and over and over until the sarcomere is at its shortest length, okay? So it doesn't all happen in one shortening. It happens progressively, progressively, progressively until the entire sarcomere is shortened.